All right, hello geometry. We are going to continue talking about probability today. Today we are going to go over compound probability and looking at and or statements involved in probability. So last time we met, we talked about theoretical and experimental probability. So what is the theoretical probability of rolling a number less than 3 on a standard dice? This should have been your warm up that you had for today. So if we think about it, how many numbers are less than 3 on our standard six-sided dice? Well, there's only two numbers that are less than 3. There's 1 and 2. So we have probability of getting a number that is less than 3 is equal to 2 out of 6 total outcomes. We have 2 desired outcomes, 1 and 2 out of our 6 total outcomes. 1, 2, 3, 4, 5, 6. And so that would be 0.33 repeating as your decimal. So that would be the theoretical probability. Now let's say I rolled 12 times and got these results. What is the experimental probability of rolling a number less than 3? Well, all we have to do is look at how many times they rolled the number was less than 3. Well, so we said it was 1 and 2, which is 3 and 0, so a total of 3 times out of 12 total options. So our experimental probability of getting a number that is less than 3 would be equal to 3 out of 12, which is the same as 0.25. And that would be our experimental probability. So once again, theoretical probability and experimental probability don't always necessarily match up, but they're typically going to be close, or they're typically not going to be too different. So we're going to jump into, once again, compound probability. When the probability of two events do not affect each other, these events are called independent events. For example, if you flip a coin and roll a dice, whatever you're doing to that coin, it's not affecting that dice roll. If I flip this coin, it's not, whether it lands on heads or tails, it's not going to affect whether my dice lands on 1, or 2, or 3, or 4, whatever. These are independent events because they do not affect each other. The result one does not affect the other. A non-example of this is if I picked a card from a deck of cards, and without replacing the first one, I pick another deck of cards. This would be an example of dependent events. Because as soon as I pick that first one, my first chance is getting a 1 out of 52 cards from my deck. I have a 1 out of 52 chance of getting, like, I don't know, an ace. An ace of spades. If I don't put that first card back in the deck, though, the number of cards in the deck now drop down to 51. So I have a different chance of getting that second card. Comparatively, if I put it back into the deck, I would have 52 chance. So this is dependent events because taking that first card does affect the result of taking the second card, while this one is independent events because flipping a coin does not affect my dice roll. So when two events are independent, the probability of both of them occurring is probability of A and B. So that's when we're looking for both of these things occurring at the same time. The probability of A and B is equal to probability of A times the probability of B. So for example, flipping a coin and landing on heads, and rolling a dice and landing on 6. So we know these are independent events because, once again, my coin flip and my dice roll do not affect each other. So let's look at the probability of getting a heads and getting a 6 on a standard dice. We have to think of what's the probability of each of these events, and then we have to multiply them together. So the probability of getting a heads, we know, is we have 1 heads out of 2 options. Then we're going to multiply that by our probability of getting a 6 on a standard dice, which we know we have 1 6 out of 6 options. So we just need to multiply these two fractions together. So 1/2 times 1 6. So we know we can multiply fractions top by top, bottom by bottom. So 1 times 1 is 1. 2 times 6 is 12. So 1/12 is our option. And you could turn that to a decimal if you'd like. So whenever events are independent, all you have to do is and you're looking for the probability of and both of them occurring at the same time. All you have to do is just multiply those two events together, which is pretty easy. Now, so sometimes we write it as the probability of A and B. Other times you'll see this, probability of A intersection B. So there's this upside down U symbol right here, and this is called an intersection. It means the exact same thing as and. You're just looking for the overlap of the two when both of them occur at the same time. So if you're trying to find the probability of A and B, you might see it in this notation. So we want to get familiar with this because this is probably how it's going to be written on the state test. If it's written mathematically compared to if it's written out, they'll probably say and in the question. So a desk drawer contains 5 red pens, 6 blue pens, 3 black pens, 24 silver paper clips and 16 white paper clips. If you select a pen and a paper clip from a drawer without looking, what is the probability of selecting a blue pen and a white paper clip? So we're looking for the probability of getting a blue pen and a white paper clip. Well, let's think, okay, how many blue pens are there in total? We had 6 blue pens out of how many total pens? Because these are going to be independent events, because as soon as I draw a pen from my deck, or as soon as I draw a pen from this desk drawer, it's not changing the number of paper clips, because I'm getting 1 pen and 1 paper clip. So they're not, drawing a pen is not affecting the number of paper clips that are in the desk. So these are independent. So we know we just have to find the 2 probabilities and multiply them together. So I have 6 blue pens out of a total of, 14 total pens? Sorry. 6 out of 14 is my probability of getting a blue pen. My number of paper clips, if I look, I have 24 silver paper clips, 16 white paper clips. So that is a total of 40 paper clips. Well, I have 16 out of 40 paper clips. So I have 6 out of 14 pens, 16 out of 40 paper clips. So my probability of getting a blue pen and a white paper clip is just these multiplied together. So I'll take 6 over 14 times 16 divided by 40. 16 divided by 40. Oh, I keep clicking the wrong button. Sorry, I'm messing up my calculator. We have 6 over 14 times 16 divided by 40, which gives us 6 over 35 as a reduced fraction, or we can just keep it as a decimal, which is 0.17 if we round to 2 decimal places. So about a 17% chance of getting a probability of getting a blue paper clip and a blue pen and a white paper clip from reaching in that desk drawer. So let's think about this. Is it possible to roll a 5 and a 2 on a dice at the same time? So I can roll a dice. Is it possible to get a 5 and a 2 to show up on the same time if I roll one single dice? Well, no. You're either going to get a 5, you're going to get a 2, or you're going to get some other number that's on that dice. So these events cannot happen at the same time, assuming you're only using one dice. If 2 events cannot occur at the same time, these are called mutually exclusive events. So mutually exclusive means they cannot happen at the same time. So if 2 events are mutually exclusive, then the probability of both of them happening at the same time is going to be 0, because we know it's impossible for it to happen. So we know it's probability of 0. So the intersection of those 2, probability of A and B. So if 2 events or if A and B are mutually exclusive, then probability of A and B, or probability of A intersection B, that intersection, is always going to be 0, just because it's impossible. So what is the probability of rolling rolling a 5 or rolling a 2 on a standard dice? We're not necessarily looking at 5 and 2, but what's the probability of getting a 5 or a 2? So we don't care if we roll a 5, we don't care if we roll a 2. So that would be the probability of getting a 5 or a 2 would be equal to. So we think about it, how 5 or 2, we have 2 desired outcomes out of 6 total outcomes. So that's just 2 out of 6, which is equal to 1/3 if we reduce that as a fraction, or 0.33 as we've seen before. So if 2 events are mutually exclusive, then the probability of getting either of them to occur is the probability of A or B, which is always going to equal to the probability of A plus a probability of B. If we think about it, 2 out of 6 is really just 1 out of 6 plus 1 out of 6, which is a total of 2 out of 6. We found the probability of A, probability of B, probability of 5, probability of 2, and just added them together. So that if 2 events are mutually exclusive, finding the OR statement is just finding the probability of one plus the probability of the other, add them together. That's called the general addition rule of probability. So the probability of A or B can also be written as this: the probability of A and B with this upside down, or this normal U symbol. This is called a union. So the probability of A union B, it just means the same thing. Probability of A or B. It's like looking for both of them at the exact same time. I don't care if I get the first one. I don't care if I get the second one. I just want to get either of them. It's even possible to get both of them at the same time. Great. So student athletes at the local high school may participate in only one sport each season. So they only choose one sport each season. During the winter season, 28% of students play basketball, and 24% of students are on the swim team. What is the probability that a randomly selected student athlete plays basketball or is on the swim team? So looking for the probability that a student plays basketball or is on the swim team. They do basketball or are on swim. Just think, okay, how many students play basketball? Well, we said 28% of students, so that's the same as 0.28 as a decimal. How many students play, or how many students are on the swim team? 24% of students. Now, because these students cannot participate in the same sport or cannot participate in two sports at the same time, we know they're either only on swim team or only on basketball. So these events would be mutually exclusive, so we can just simply add them together, and that would be our total result. So 28 plus 24 is going to be our result, which is going to give us 52 or 0.52 or 52% of our students. So the probability of randomly selecting a student and getting a student that plays basketball or is on the swim team is just going to be 52%. Just had to add them together. Now, what if two events can occur at the same time? For example, rolling an even number or getting a multiple of 6 or getting like a 6 on a 6-sided dice. So if two events can occur at the same time and you're looking for an or statement, these are called overlapping events. So let's try to calculate this. Rolling a 6 or getting an even number. So I'm looking for the probability of getting an even number or getting a multiple of 6. Now, if I think about it, if it's a 6-sided die, the only number that's a multiple of 6 on my 6-sided die is 6. So it's really just asking for probability of getting a 6. But what even numbers do we know? Well, if we think about our even numbers are 2, 4, and 6 on a 6-sided dice. So that's 3 out of 6. My probability of getting a 6 is just 6, so it's 1 out of 6. So if I were to add those together, that would give me a total of 4 out of 6 options. But if you look at this, we said our even numbers are 2, 4, and 6. My probability of getting a 6 is just my 6. I counted 6 twice in here, but there's only one 6 on this dice. So the probability of getting a 6, whether it's for an even number or whether it's for overlap or whether it's for getting my multiple of 6, the correct probability should be 3 out of 6 because I counted 6 twice. So whenever we are doing these overlapping events, whenever we're looking for the probability of A and B, it's always going to be the probability of the first event, which we said was our even, which is 3 out of 6, plus our probability of our second event, which was getting a 6, minus the probability of the intersection of the two, minus the overlap of the two, because you're always counting that overlap twice. So it's the probability of the first event plus the probability of the second event minus the overlap of the two, so you don't count it twice, because we counted 6 twice, so we need to subtract the overlap, which is once again just 6. We need to do minus 1 over 6, and this would be our correct probability, which is 3 out of 6. So 3 out of 6 plus 1 out of 6 minus 1 out of 6 is 3 out of 6, which is the same as 0.5 chance. So this here is a big important rule. This is a big rule. This is also given to you on your state test, which is really nice, but that's a big rule. That's our general addition rule. So remember this rule right here. So let's say we had the letters A through G in like a bag, and you're looking for the probability of getting a letter from the word face or a letter from the word cab. What would that probability be? So probability of getting a letter from the word face or cab. Well, one easy way to help us with this, rather than just counting, because if I try to count my letters from the word face and my letters from the word cab, I have some overlapping letters there. One easy way to do this is create a Venn diagram and see, okay, what letters are in the word face, what letters are in the word cab, what letters are in both, and then I can just count my total, and that's one way of looking at this. And we can also use this to help us with our general addition rule. So if I look at the letter A is in both face and cab, B is in the word cab, C is in both of them. D is in neither of them. E is in face. F is in face. And G, once again, is in neither of them. So if I look, my total number of letters I have is 1, 2, 3, 4, 5 out of 7 letters. So I would have 5 out of 7 I know should be the probability. Another way we could have calculated this is we could think, okay, how many letters do I, because we know these are overlapping events, our probability should be probability of face plus the probability of cab minus the overlap of the two, the face and the cab words. Probability of F intersection. I don't have my intersection letter copied. Sorry, let me grab this. E would be minus the probability of getting an intersection of face and cab. Well, if we think, how many letters do we have in the or how many probability of getting a letter from the word face? Well, we have 4 out of 7 letters in face. What's my probability of getting a letter from the word cab? Well, I have 3 out of 7 in cab, minus the overlap of the two, which I see I have 2 letters that are overlapping, which are counted twice. They're counted in the word face and they're counted in the word cab. So it'd be 3 out of 7 plus, or sorry, 4 out of 7 plus 3 out of 7 minus 2 out of 7, which is going to give us a total of 5 out of 7 probability, which once again matches. So if you need to, creating a Venn diagram like this in certain situations can be helpful for finding these OR statements, with finding these unions, because you can see where that overlap is. So you can take the probability of one plus the probability of the other minus that overlap of the two events. So that's why Venn diagrams are always helpful with probability. All right, these will be our last 2 questions. I have a bag of I have a bag with each letter of the alphabet in it. What is the probability of picking a letter from the word vowel or getting a letter from the word math? So I know my general addition rule tells me that if I'm getting a letter, let me copy my union symbol. So I'm looking for the probability of getting a letter from the word vowel, or getting a vowel, or getting a letter from the word math. I think, okay, first let's think, because it's a union, we know we're doing the probability of A plus probability of B minus the overlap of the two. Now, how many vowels do I have? Well, I have 5 vowels, A, E, I, O, U. We're not worrying about Y, because it's not necessarily a vowel in this situation. So probability of getting a vowel is 5 out of 26 total letters. What's my probability of getting a letter from the word math? Well, I have 4 letters in math, M-A-T-H, so that's going to be 4 out of 26. And then I have to think, okay, what is the overlap of these two? Where do these two overlap? Well, I have to think if it needs to be a vowel and in the word math. They have to happen at the same time. So my vowels that are also in the word math is just A, so 1 out of 26 letters. So if I add these together, I have 5 plus 4 minus 1 out of 26 is going to give me a total of 8 out of 26 letters, which I can also turn that into a decimal if I like, or reduce it. 8 out of 26 turns into 0.31 if we rounded the nearest 100th place. So about 31% of our chance of getting either a vowel or a letter from the word math. So let's find the probability of rolling either an odd number or a number that is less than 4 on a standard size dice. So I'm trying to get an odd number or a number that is less than 4 on my dice. So if I think, how many odd numbers do I have on my standard size dice? Well, I have 3. I have 1, 3, and 5. So I have 3 out of 6 on my standard dice. How many numbers do I have that are less than 4 on my standard size dice? Well, numbers that are less than 4 are 1, 2, and 3. So there's another 3 out of 6 chance. And then once again, we have to think, what is the overlap of the two? What's the intersection? What are my odd numbers that are also numbers that are less than 4? Well, 1 and 3 are both odd numbers, and they're also less than 4, so that's a 2 out of 6 that I need to count, that I counted twice, that I have to get rid of. So I have 3 out of 6 plus 3 out of 6 minus 2 out of 6, which is going to give us 4 out of 6, which is going to be equal to 0.67 as a decimal. So 67% chance of getting either an odd number or a number that's less than 4. All right, so quick recap. We went over a little bit today, so here's our quick recap. So independent events. If two events are independent, they do not affect each other. So the probability of A and the probability of B is always going to equal to the probability of A times B. So if two events are independent, the intersection of the two is then multiplied together. If two events are mutually exclusive, which means they cannot happen at the same time, then the probability of the intersection is always equal to 0. There is no intersection because they don't overlap. But if the probabilities can overlap, the probability of A and B, the probability of the OR statement is going to be the probability of A and the probability plus the probability of B minus the intersection of the two, minus the probability of A and B. So it's always take the first event plus the second event minus the overlap of the two is for our unions. But once again, we want to get familiar with these. So these intersections mean A and B, while the unions mean A or B. So anytime you see this upside down U, it means or. Anytime you see this, anytime you see this union symbol, the normal U, it's or. Anytime you see this upside down symbol, it means and. And that's pretty much what we went over today. So you have some practice over this. You'll look at independent events, mutually exclusive events, and statements or statements. And then you'll also look at a Desmos activity after that as well. Let me know if you have any questions. Have a great rest of your day. Oh, I forgot to click the wrong button on here. There we go.